The last section we're going to study for Chapter 5 is Section 5.3, and that is on what's called independence and the multiplication rule, and it starts on page 258. So independent events. So first thing we need to learn, the two events are considered independent if knowing the outcome of one does not change the probability of the other. So if I flip a coin the first time and it lands on heads, knowing that it landed on heads does not change the probability that it's going to land on heads the next time. So those are independent events. Two events are considered dependent if knowing the outcome of one does change the outcome of the other. So if you play blackjack or poker with a deck of cards, every time a card is flipped over, the probabilities have changed. And so those events are dependent on each other every time you flip over a card. So those are dependent events. So here's some examples. First question, does knowing a coin landed on heads the first time change the probability that it will land on heads the second time? No. If the answer is no, you have independent events. If you play roulette on the big wheel that spins and they throw the marble in there and it lands on different numbers, there's a big sign on the side that shows you all the different numbers it's landed on recently. And I see a lot of people looking at that, and it always cracks me up because it has nothing to do with the next roll. Every time that marble is thrown and the wheel is spinning, it's an independent event. It doesn't matter what the previous landings were. Anyway, that's another example of independent events. So does knowing that a die landed on 4 the first roll change the probability of it landing on 4 the second time? Does it change the probability of landing on 4 the second time? No. These are independent events. And number 3, is knowing that a clubs was drawn the first time from a deck of cards and not put back, does that change the probability of a clubs for the next draw? Well, yes it does. If I get a clubs and I don't put it back, it has changed. So if the answer is yes, these are dependent events. Usually with a deck of cards, every time a card is drawn and not put back, all the probabilities have changed. And so usually when you're dealing cards or playing a card game, every time you flip over a card, the probability of what's left in the deck has changed. And then you flip over another card, all the probabilities have changed. And as you flip over cards, the probabilities keep changing. And so generally with card games, those are all dependent events, and the probabilities get very complicated very quickly depending on what was drawn. All right. So what does this have to do with probability? If the events are independent, we can easily calculate various probabilities. If the events are dependent, it is almost impossible to calculate various probabilities because they're constantly changing depending on what happened previously. So at casinos, they usually have about 10 decks of cards in what they call a shoe because they want those probabilities to be constantly changing. They don't want anyone to be able to predict what might happen. So they're all dependent events. For our purposes, we're going to stick with independent events, and we're not going to worry about dependent events. We need the events to be independent so that we can easily calculate the probabilities. All right. So the multiplication rule for independent events. If you toss a fair coin twice, what is the probability of it landing on heads both times? We will write that the probability of heads the first time and heads the second time. So it's not or, it's and. Heads the first time and heads the second time. Since these are independent events, you can multiply their individual probabilities. So the probability of getting heads the first time is 1 out of 2. The probability of getting heads the second time is 1 out of 2. 1 out of 2 times 1 out of 2, for multiplying fractions, we multiply tops and bottoms, is 1 out of 4, or 0.25. So the probability of getting heads both times, the first time and the second time, you multiply those probabilities together and get 0.25. So the multiplication rule for independent events, the probability of E and F, is the probability of E times the probability of F. This could be true for a whole bunch of events, an unlimited number of events. You just multiply, however many events you have. And. You want all these things to happen, you just multiply them all up. And these are both in your booklet, both of them. They say the same thing. This is for 2 events, this is for multiple events. All right. So here's a couple examples. What is the probability of a die landing on 4 3 times in a row? So I have 1, 2, 3 times. The first time it has a 1 out of 6 chance of landing on 4. The second time it has a 1 out of 6 chance of landing on 4. And the third time it has a 1 out of 6 chance of landing on 4. Each roll is independent, so I multiply them together, and I get 1 out of, I believe that's 216. Let me just make sure. And 1 out of 216 is 0.0046. Very small chance that it's going to land on 4 3 times in a row. Part B, what is the probability of the die landing on 4 10 times in a row? Well, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1 out of 6 each time. Multiply them all up. A quicker way to do that is 1 out of 6 to the 10th power, which is 1 out of, this is a big number, 604,66176. That's a huge number. You're going to get a very tiny number. So if you do 1 out of 604,66176, you get this that e to the negative 8. That means we're going to move that decimal point 8 times to the left, which is 0.000000165. Essentially 0. Not going to happen. The probability of a die landing on 4 10 times in a row, not going to happen. 0. If you play the lottery or scratch-offs, these are pretty much your odds of winning. Pretty much nothing. So just always keep that in mind when you buy a scratch-off or play the lottery. Your chances of winning are just about nothing. All right. And now we have the at least probabilities. This is the most confusing concept for this chapter. So I'll really take my time here. If you see the phrase at least 1 used in a probability question, the complement rule can come in handy. The complement rule can come in handy, and I will try my best to explain this. I always have students very confused by this. Try to keep general as best you can. Don't get too tied down in things. So the probability of at least one thing happening, that means once or twice or 3 times or 4 times, is 1 minus the probability of not at least one thing happening. Remember, the probability of an event is 1 minus the probability of that event not happening. So that's the complement rule. Saying not at least one really means none. That's really what it means. If I have not at least one person passing, I don't even have one person passing, that means I have no one passing. So try to think about it like that. Not at least one means none. So the probability of at least one is 1 minus the probability of none. And one and none kind of rhyme, so it might help you remember that. The probability of at least one is 1 minus none. So, using that idea, hopefully that made a little bit of sense. It's on page 261 if you need some more clarification. This example, I think hopefully will clear it up. Dr. Pepper advertises that 15% of bottle caps have a winning code underneath them. If you guys remember, you flip over, you enter the code online, and you might win something. So if you buy a 6-pack of Dr. Pepper, what is the probability of at least one bottle cap being a winner? So we said the probability of at least one is 1 minus the probability of none. None would be none winning. If none of them are winning, that means they're all losing. So far, so good, hopefully. If none of them win, that means they all lose. So the probability of at least one is 1 minus the probability of all 6 Dr. Pepper bottles, all 6 of them losing. So you have to use the complement rule. If there's a 15% chance of winning, there's an 85% chance of losing. So the first bottle has an 85% chance of losing. The second bottle independently has an 85% chance of losing. And the third one, and the fourth one, and the fifth one, and the 6th one. This is getting repetitive. Every single bottle is going to lose. None of them winning would be all of them losing. All of them losing. Well, that's 1 minus the probability of 0.85. Don't need the p anymore. 1 minus 0.85 to the 6th power. Because we want all 6 to lose. So 1 minus 0.85 to the 6th power. You just type that in like that. And you get 0.6229, which is just about 0.62 or 62%. So the probability that you have at least one bottle cap that's going to win is about 62% chance. That, I would say, is pretty good. But this gets complicated because you have to remember this. You have to remember that you're doing the opposite of what they tell you. So if they have a 15% chance of winning, they have an 85% chance of losing, and you want every single one of them to lose, and you do 1 minus losing, and that will give you at least one winning. If that's a little confusing, I can give you more examples. There are more examples in the book. This one is not in the book. This is one that I use to hopefully help it make sense. But there are more in the book if you need to see more examples. All right. So this is kind of a nice summary of everything that we need to know from sections 5.1 through 5.3. We know that probabilities have to be between 0 and 1. The sum has to add to 1. Remember, we use the summation symbol. If they are disjoint events, the or probability, you just add them together. If they are not disjoint events, remember you have to subtract the overlap. Then the complement rule. The probability of the complement is 1 minus the probability of the event. The way I like to remember it is the probability of the event is 1 minus the probability of the event not occurring. That might be another way. It's the same equation, just rearranged. And then if E and F are independent events, then the probability of E and F, you multiply them together. So that's a nice summary chart of everything we need to know for Chapter 5. Remember, we're only doing sections 5.1 through 5.3. So if you do practice quizzes and tests, you'll stop about halfway through them.